He's a distinguished scientist of the ACM. He received his PhD from Stanford University and his bachelor from the National Taiwan University. Please let's welcome Yung-Hsiang. Yung-Hsiang, you have the platform.
Can you see my screen now?
Yes, I can see your screen.
Well, thank you very much. All right. It is the year 2000, everything's possible. All right, thank you very much. Today I will talk about some of our recent work on modular neural network for low power image classification on embedded devices. First, this is the year 2000, and I want to share express my gratitude to the people that make our life safe and possible. I always actually spend a few minutes talk about some of our current work on fighting against the pandemic. In March, when the United States was closing down, I reconfigured my research team to try to figure out what we can do for improving our understanding about how people react to the pandemic. So one thing we have done is to use publicly available data and understand how people respond. As you can see on the left side, it's an image from New York. And you can see we mark people close to each other in red boxes and people far away by the green boxes to indicate whether people are doing social network distancing. The right side is the best method at that time. Social distancing was not a research topic until recently. So the best method was unable to find anything meaningful. And this is another example that shows the contrast between 2019 and 2020. As you can see in New York, 2020, it's pretty much empty. So we are really living a different world. This is the number of cameras we discovered on the internet. They provide real-time data. And this is something I think pretty interesting for us to look at. These different colors show different stages of lockdown. Different countries have different phases of opening. For example, Germany has a two-phase reopening, and Australia has one-phase reopening. So horizontal axis shows how many vehicles we detected during this period of time, and the vertical axis shows how many people we detected over those public cameras. As you can see, a pretty clear pattern as the countries reopen. We see a lot more people and a lot more cars, except the only exception will be Great Britain. It's not clear there is a clear distinction between the different phases. So I hope this gives you an idea how we can use our technologies to contribute to the world welfare. So there are some papers and some patterns showing how we conduct this work. Now let me go to the real topic of today's discussion is neural network, modular neural network, how we construct a hierarchical neural network to do computer vision more efficiently. This presentation will talk about what's modular neural network and how we can train them, and how we can use that for image classification, show the experiment. And I will also talk about IEEE competition that has been going on for several years. Then I will conclude. First is some of our recent papers. It's a recent paper published in IEEE Transaction on Design Automation and the Design of an Electronic System. And another paper in Symposium on Low Power Electronics. And then the third is a survey paper of deep learning, efficient deep learning methods. So let me explain what the modular neural network means. If over the presentation, you want to remember only one slide. So I understand everybody here has been listening to many presentations. But if you want to remember one slide, this is the slide you want to take away. When we talk about neural network, we often think about neural network as a big black box with a lot of data coming in, and somehow magically some result come out. We heard quite a few speeches today about, for example, quantization, about pruning, and so on. Try to make them more efficient. But we are looking at a somewhat different approach. can we break one big neural network into many smaller neural networks? Instead of trying to do many things at once, we try to do a few small things separately. And the advantage of a smaller neural network is each neural network need to do fewer things. It doesn't need to do get all the data from the image all the way to the labels. Instead, some of the neural network only need to take images and break into some smaller group of images. Then the next neural network will take that smaller group and do further classification. As a result, each neural network can be much simpler. Here I use the example of a truck, car, cat, and dog as examples. If you have these 4 input, you want to classify them into different labels. Then one way you can do it is the first method, that's the traditional method, is you have a big neural network that give you one of 4 labels. The second method is the method on the right. You first break them into vehicles or animals. Then you further classify them into truck or car or cat. To classify vehicles, you don't really care about animals. Then you can stop after the first classification, and you don't have to spend time or energy to distinguish cat and dog. So that's the basic idea of a modular neural network. If you are interested in trying it out, the source code is at the bottom. So I don't think I need to explain to people computer vision is very energy hungry, and in fact, I find quite interesting. There are quite a few pictures online showing how they cook.
Excuse me, Yung-Hsiang. It seems that the sharing of the screen is failing. Can you stop the sharing and start again? We
Okay.
cannot see anymore, fortunately.
All right. So let me try it again. Okay. Okay. Does it work now?
Still, unfortunately, not. We only see black screen.
How about you share? Somehow I'm not sure what's happening. I sent you the link.
I got the link. I need that you give me privilege because I cannot access the presentation.
Okay, so let me do it again. Okay. Oh, I see. I didn't allow everybody to, yeah.
Okay, now I can see it. Let me share my screen so I can continue the talk.
All right. Thank you
Sorry for the glitch. Okay. Let me know if that's working. Are you guys able to see my screen?
I cannot.
Not yet?
Can you see my screen?
No, unfortunately, we can only do one at a time. If you want to try it again to show your screen, that might be even better.
Okay, I stop now.
You yes, start sharing your screen? Okay.
Do you want to share or?
Please go ahead. It's better if you share your screen so you can traverse the slides as you please.
That's very strange. Can you show my screen?
I'm not able to see your screen just yet.
Okay, then how about you share?
Okay.
Or people can see the slides on their computer since I share the slides. This is very strange. I had the speeches a few days ago.
All right. Let's see. Let me open the presentation.
Should I exit Spotlight?
You can exit the Spotlight. Should be.
Okay. It does not allow me to exit Spotlight.
Sunny, can I try?
Go ahead.
Let me know if you can see where my slide.
I can see it.
Yep.
Okay, which slide should I be in?
Slide 11, but I cannot see it.
You should be able to see on the Teams Let me remove it from the spotlight. So.
Okay, then in that case, I will just ask you to go to next slide. I apologize for the problem. Can other people see the slide?
I can see the slide. He is on slide 11.
Yes, I can see.
Okay, now it's slide 11.
Mm-hmm.
Okay, so computer vision is energy hungry, and people know that already. I'm going to skip the next slide as a joke. So slide 13, why do we need low power computer vision? We're looking at many applications such as mobile phone, or even use solar power for computer vision. So let's move to slide 14. Let's start getting into some more technical details. This slide shows different type of a method for computer vision. As you can see, the right side of the two bar of ResNet and the condensed net, they have a much better accuracy, but they also have much higher complexity and computation. In fact, last year, slide 15, a report by MIT Technology Review says that training a neural network can emit as much carbon as 5 cars in their lifetime. So that's very significant. So we want to understand how we can make neural network more energy efficient. Now let's move to slide 16. The reason neural network consumes a lot of energy is the following. First, there are a lot of parameters. Neural network can have millions of parameters, and often those parameters cannot fit in memory, so cannot fit in cache. So there's a lot of memory access. And to go through those parameters, they are a lot of computation. As a result, is high energy consumption and low inference speed. What we want to do in this work is to use modular neural network to reduce energy consumption. We want to reduce the number of parameters. We want to reduce the number of operations, but we still want to maintain the accuracy of the neural network. Now let's move to slide 18. So I explained this before. This is a review what modular neural network means. So let me get into the details how we can create this modular neural network. First, we can imagine a modular neural network as the original big deep neural network, but divided into different modules. Each module starts with a convolution layer and go to the fully connected layer. It's similar to a traditional neural network. However, the outputs are not labels. The outputs are the inputs to the follow-up neural networks. That way, we don't have to recompute what has already been computed. So you can think of the neural network from the root to the leaf as the original, the deep neural network. But as I mentioned earlier, in many cases, we don't have to do all the classification all the way to the end. That's why this tree may not be full. The leaf nodes may have a shorter distance to the root. Now let's move to slide 20. So when we want to construct a neural network, we basically need to solve 3 problems. The first problem is we have to decide which information will be grouped together. As I showed earlier, we want to put a truck and a car together in the same group. We want to put a dog and a cat in the same group. How do we make that decision? So that's the first problem we need to solve. The second problem we need to solve is how can we make each module small? Should we start from the smallest and gradually grow, or should we start from a very big neural network and gradually shrink it? And that's the second problem. Then the third problem is how do we train those modules? So let me get into the individual questions. Now we are moving to slide 21. The first question we encounter is how do we determine how to group the different concepts? Earlier, I mentioned that we want to put truck and a car together in the same group. We consider different methods. This slide shows 2 methods to group different information together. The first is called visual similarity. The second is called semantic similarity. If you think about visual similarity, we'll consider a bird and an airplane to be visually similar because both of them have wings, both of them are in the sky. But they are semantically dissimilar because a bird is an animal, an airplane is a machine. Therefore, they are not really the same kind of things. In contrast, we think about a banana and an apple. Both are fruit, therefore they are semantically similar, but they are visually dissimilar because the banana is a long shape, an apple is a round shape. We have done some experiment with different metrics of similarity, and we find visual similarity is a better method to group different categories of information. Based on visual similarity, we'll actually put a plate and a pizza together into the same group because they are visually similar. Both of them are some kind of round shape. We further analyze, now we go to slide 22. We further analyze different categories of information, and this slide 22 shows that the cat, dog, bird, deer are very similar. It's hard to distinguish them. In contrast, truck and automobile are far away. So what does this mean? This means that we can use a simple module to distinguish truck and automobile from cat, dog, bird, and a deer. So now we have two groups. We can separate them pretty easily. And this module can be very small. On the right side of the slide, as you can see, I already explained that the pizza and the plates are semantically dissimilar, but they are visually similar. Now, how do we classify them into the same group or different groups? The slide 23 shows that we use an existing pre-trained large neural network to guide us. For example, we put an airplane image into a large neural network and look at the softmax layer output. Then we consider the softmax layer output. If they are similar, then we will put into the same group. The output of softmax layer, then we put into a sigmoid function. Then we discover a ship, an airplane, and an airplane are actually very similar. If you compare with other shapes, other type of visual information, airplane and the ship, they are long shapes, right? Compared with other kind of images such as bird or cat, they are usually not a long shape. As a result, we use this to determine airplane and the ship should be in the same group. So we answer the first question, how do we group them? We group them based on the softmax output and then use visual similarity instead of semantic similarity. The second question is, how do we determine the size of each module? Instead of taking a big neural network and try to shrink it, we go the other way. We take a smaller neural network and try to grow it. So what does this mean? We start from, okay, you are one step behind. I'm now in slide 24. I think the button is wrong. I guess it did not show the slide for the first slide. Therefore, right now the title of the slide is trade-off between accuracy and memory.
Okay, I think now it's showing the trade-off between accuracy and memory.
Okay, thank you. So what we do is we start with a small neural network and we add more layer and see whether we get better accuracy. And we stop once the accuracy seems to have a diminishing return. As you can see in this slide, we start with a small neural network and we grow it. And once we grow to a point where the accuracy no longer increases dramatically, then we stop. So that answers the second question, how we determine the size of a neural network. And we do that for each module. This actually is now the next slide, it's a flow chart, shows that how we determine the size. We choose the accuracy and the size of the memory. We compare. If we grow the size, so that's the accuracy, AI plus 1 minus AI, that's the improvement in accuracy. And divide by the increase the size. If it's greater than a threshold, that means increasing the size has a significant benefit, then we grow the size. Otherwise, we stop, means now we hit diminishing return, so we shouldn't grow the size any further. The next slide, let me explain how we train it. The training method is actually very similar to existing method. We do use backpropagation. So if you look at this modular neural network, it's actually very similar to the original big deep neural network. So we propagate from the output backward layer by layer. So the training method is actually very, very similar. We do not have to invent a new method. So now let me move to the next slide. That's how we actually build a tree. There are 4 steps. Right now, the title is Construction of the Modular Neural Network-Tree. We choose the size. As I mentioned, we start from small and gradually grow. Then we find similar groups using the softmax layer. Then we train, and we repeat this process until we reach the desirable accuracy. The next slide shows that what we discovered using the CIFAR10 dataset. As you can see from this slide, we do not set restriction about the fan out. A module can have 4 children, or 3 children, or 2 children. We do not set a limitation. Instead, the limitation is set by the the visual similarity. From the data, we can see that from the root, it actually breaks into 3 different groups. The first group, called SG1, we call supergroup. SG means supergroup because we consider truck or an automobile as 1 group, 2 groups. So supergroup 1 actually contains truck and automobile. And supergroup 2 contains airplane and ship. Supergroup 3 contains the animals, but they are too close to be classified in 1 single module. So we further classified them into supergroup 4 and 5. In supergroup 3, we can directly classify them into frog or horse. But if we want to classify as cat and dog, then this particular supergroup 3 will be too big. So instead of using a big neural network for supergroup 3, now we break into supergroup 4. So if you look at from the root to supergroup 4, that's a deep neural network. So we allow the neural network to be deeper or shallower based on how easy we can classify the data. At the bottom, you can see the decision method. We select a child module. If the child module is a leaf node, that means we're done. We have a classify them. Otherwise, we'll continue going down the tree. The next slide shows how we set up the experiment. As you can see in this slide, we actually have 2 set of machines. The study boxes are running on the desktop GPU for the training and the building the tree. Then the dash box are that run on an embedded system. We use Raspberry Pi for the measurement of power and performance. The next slide shows a comparison, that's slide 30, of existing methods. On the left side, you see that we have 2 groups of a data set. We have CIFAR10 and ImageNet. Then we compare our method with VGG16, ResNet, DenseNet, MobileNet, and so on. Our methods are highlighted at the bottom of each category of data set. We have a much smaller model size. These model sizes are all the modules add together. And we also have much smaller number of operations. In terms of accuracy, we have a little bit loss of accuracy. As you can see, for CIFAR10, our error rate is a bit higher. And in ImageNet, our error rate is better than SqueezeNet, but worse than state-of-the-art. So that's something we are still working on, how to make them as accurate as the best. But in terms of size and number of operations, we are orders of magnitude smaller. We also compare our method with some other existing method. The hierarchical techniques, you can see the reference at the bottom. our method, some of the method, we do not have the source code, so we cannot measure it. As a result, we leave the cell to be blank. As you can see, our method has much better test error. It's much better than other methods. And we also try our method across different data sets, including CIFAR-10, Caltech 101, and ImageNet. In terms of performance and energy measured on Raspberry Pi, we actually have done that on Raspberry Pi 3 and Raspberry Pi 0. You can see VGG condensed net and our modular neural network tree, we have much smaller inference time and also much smaller energy consumption per image. So that is our modular neural network. I'm going to use the next few minutes to promote a competition we've been organizing since 2015. And this is this year's competition. If you are interested, you can go to the website called lpcv.ai. And PyTorch is actually one of the sponsors. I'm going to skip, so I'm going to slide 35 now. So this year, there are 3 tracks. The first track is a UAV video. So basically, competition need to recognize words that's captured in video by a drone. The next track is an FPGA image using the Xilinx board. Then third is using TensorFlow for image classification or object detection. And if you go to slide 35, PyTorch has already decided to sponsor another competition for next year. This competition will be multi-object tracking. As you can see, there will be people holding balls and they will pass the ball. The vision problem is to track who is holding the ball. Something like the table shows. At a particular frame, you'll say which person, each person has a number, is holding the ball. So that is the competition for next year. We will announce this competition after some more details are decided. Now let's go to slide 37. We are still looking for sponsors. So if you are interested in sponsoring next year's competition, please let me know. Slide 38 shows my graduate students. As everybody knows that the real work is done by students. So I want to appreciate the students' great work. So let me go to slide 39, the conclusion. I have presented a new method to think about how to save energy and improve performance using a concept called hierarchical neural network. Instead of using one big neural network, we want to use several smaller neural networks to reduce the number of operations, reduce the memory requirement, reduce energy consumption, and still maintain the accuracy. The concept of hierarchical neural network is each small neural network, we need to do only a few things, only classify into several categories. And as we go deeper, we can classify them into more difficult problems, such as distinguish dog and a cat. But however, we don't have to use a big neural network to distinguish between truck or cat. So that concludes my presentation. Thank you.
Thank you, Yung-Hsiang. I think we have time for 1 or 2 questions. Is there any questions? I have one question. So it seems that you have targeted a specific size of network. Is there any limitation to the size of parameters of the target network to be effective for this approach?
What do you mean by size?
The size of the parameters are you talking about? It can be, you can define that by the specific number of the parameter size of the model. You can define that in terms of the layers, if that makes it much simpler to definition of the model. But I'm more curious about the constraint of the spectrum of the model size, that this approach can be very suitable.
We do not constrain. The size is determined by the method we build a neural network. If the data, and that depends on the data. If the data is more complex, the neural net, the hierarchy will be deeper. For example, if you consider CIFAR-10 versus ImageNet, the ImageNet neural net will be bigger. And we do have a constraint on the hardware we want to port on the Raspberry Pi, but that's a consequence of our optimization. It's not a constraint we put into our system.
Get it. All right. Is there any other questions? There is one question. Satyam?
Yeah, hi. Yeah, welcome. So the question is, I think low power computer vision is definitely very important for, especially for the edge device. So can you give us some direction, like what is the status as you are aware, and what is like a most important thing or most challenging thing you think to make the computer vision more portable and also can be like a large size used in edge device?
Okay, thank you for the question. I'm not sure I'm the most qualified person. There are a lot of experts here, but I will throw some ideas here to start the discussion. I think a lot of things can be improved by spatial purpose. We are looking at, my own research team is looking at some spatial purpose computer vision. Let me use an example. I'm working with some people for safety in factory. Your computer vision for factory safety doesn't need to be able to tell there's an elephant in a factory, right? So you can, what I mean by that is you can reduce your data input dramatically based on the spatial your need. And as a result, your computer vision can be much smaller. The common approach people use is to do general purpose, and they are, for example, each ImageNet has 1,000 categories. That's great for general purpose. But if you have a specific application, then spatialization usually can give you a lot of advantage.
Okay,
We have
thank you.
one more question. So Ahmed?
Yes, great
Go ahead.
Yep, it's very interesting. So
Thank
my
you.
question is, so you're running it in a hierarchical manner, but do you have to run them in sequence, like sequentially, or can you parallelize the workloads?
The work we have done so far is sequential. So basically you take one and go to the next module, go to the next module. We're working on parallelization right now.
Okay, so
yeah.
if I have two hardware platforms, I can run them in parallel.
It should be, but we have not done that yet.
Okay, thanks so much.
Yeah, that's another good point, that this approach actually can make a parallelization easier, but we have not done that yet. If actually my student is here listening, after he finished parallelization, he can graduate.
Thank you. Thank you, Yung-Hsiang. That was a great presentation. Apologies
Thank
for
you.
the
I
glitches.
apologize for the technical difficulty. Thank you.
No problem.